The AIM-9 Sidewinder is a short-range air-to-air missile developed by the United States Navy in the 1950s. Entering service in 1956, variants and upgrades remain in active service with many air forces after 5 decades. The United States Air Force purchased the Sidewinder after the missile was developed by the United States Navy at China Lake, California. It is one of the most widely used missiles in the world, equipping most Western-aligned air forces and, through the K-13 version, many former Soviet-aligned forces as well. The majority of Sidewinder variants utilize infrared homing for guidance. The AIM-9C variant used semi-active radar homing and served as the basis of the AGM-122 sidearm anti-radar missile. The Sidewinder is the most widely used missile in the West, with more than 110,000 missiles produced for the U.S. and 27 other nations, of which perhaps 1% have been used in combat. It has been built under license by some other nations including Sweden. The missile was designed to be simple to upgrade. The United States Navy hosted a 50th anniversary celebration of its existence in 2002. Boeing won a contract in March 2010 to support Sidewinder operations through to 2055, guaranteeing that the weapons system will remain in operation until at least that date. Air Force spokeswoman Stephanie Powell noted that due to its relative low cost, versatility, and reliability, it is very possible that the Sidewinder will remain in Air Force inventories through the late 21st century. Design. The AIM-9 is made up of a number of different components manufactured by different companies, including Aerojet and Raytheon. The missile is divided into 4 main sections: guidance, target detector, warhead, and rocket motor. The guidance and control unit contains most of the electronics and mechanics that enable the missile to function. At the very front is the IR seeker head utilizing the rotating reticle, mirror, and 5 CDS cells or pan and scan, focal plane array, electric motor, and armature, all protruding into a glass dome. Directly behind this are the electronics that gather data, interpret signals, and generate the control signals that steer the missile. An umbilical on the side of the GCU attaches to the launcher, which detaches from the missile at launch. To cool the seeker head, a 5,000 psi argon bottle is carried internally in Air Force AIM-9L variants, while the Navy uses a rail-mounted nitrogen bottle. The AIM-9X model contains a Stirling cryo-engine to cool the seeker elements. 2 electric servos power the cannods to steer the missile. At the back of the GCU is a gas grain generator or thermal battery to provide electrical power. The AIM-9X features high off-bore sight capability, together with JHMCS. This missile is capable of locking onto a target that is in its field of regard, said to be up to 90 degrees off-bore sight. The AIM-9X has several unique design features including built-in test to aid in maintenance and reliability, an electronic safe and arm device, an additional digital umbilical similar to the AMRAAM, and jet vane control. Next is a target detector with 4 IR emitters and detectors that detect whether the target is moving farther away. When it detects this action taking place, it sends a signal to the warhead safe and arm device to detonate the warhead. Versions older than the AIM-9L featured an influence fuse that relied on the target's magnetic field as input. Current trends in shielded wires and non-magnetic metals in aircraft construction rendered this obsolete. The AIM-9H model contained a 25-pound expanding rod blast fragmentary warhead. All other models up to the AIM-9M contained a 22-pound annular blast fragmentary warhead. The missile's warhead rods can break rotor blades. Recent models of the AIM-9 are configured with an annular blast fragmentation warhead, the WDU-17B by Argotech Corporation. The case is made from spirally wound spring steel filled with 8 pounds of PBXN-3 explosive. The warhead features a safe, arm device requiring 5 seconds at 20 grams acceleration before the fuse is armed, giving a minimum range of approximately 2.5 kilometers. The Mk-36 solid propellant rocket motor provides propulsion for the missile. A reduced smoke propellant makes it difficult for a target to see and avoid the missile. This section also features the launch lugs used to hold the missile to the rail of the missile launcher. The forward of the 3 lugs has 2 contact buttons that electrically activate the motor igniter. The fins provide stability from an aerodynamic point of view, but it is the roller ends at the end of the wings providing gyroscopic precession to free-hinging control surfaces in the tail that prevent the missile from spinning in flight. The wings and fins of the AIM-9X are much smaller and control surfaces are reversed from earlier Sidewinders, with the control section located in the rear, while the wings up front provide stability. The AIM-9X also features vectored thrust or jet vane control to increase maneuverability and accuracy, with 4 vanes inside the exhaust that move as the fins move. The last upgrade to the missile motor on the AIM-9X is the addition of a wire harness that allows communication between the guidance section and the control section, as well as a new 1760 bus to connect the guidance section with the launcher's digital umbilical. The Sidewinder incorporated a number of innovations over the independently developed World War II-era Madrid IR range fuse used by Messerschmitt's Enzian experimental surface-to-air missile that enabled it to be successful. The first innovation was to replace the steering mirror with a forward-facing mirror rotating around a shaft pointed out the front of the missile. The detector was mounted in front of the mirror. When the long axis of the mirror, the missile axis and the line of sight to the target all fell in the same plane, the reflected rays from the target reached the detector. Therefore, the angle of the mirror at the instant of detection estimated the direction of the target in the roll axis of the missile. The yaw pitch direction of the target depended on how far to the outer edge of the mirror the target was. If the target was further off axis, the rays reaching the detector would be reflected from the outer edge of the mirror. If the target was closer on axis, the rays would be reflected from closer to the center of the mirror. Rotating on a fixed shaft, the mirror's linear speed was higher at the outer edge. Therefore, if a target was further off axis, its flash in the detector occurred for a briefer time, or longer if it was closer to the center. The off-axis angle could then be estimated by the duration of the reflected pulse of infrared. The Sidewinder also included a dramatically improved guidance algorithm. The Enzian attempted to fly directly at its target, feeding the direction of the telescope into the control system as if it were a joystick. This meant the missile always flew directly at its target, and under most conditions would end up behind it, chasing it down. This meant that the missile had to have enough of a speed advantage over its target that it did not run out of fuel during the interception. The Sidewinder is not guided on the actual position recorded by the detector, but on the change in position since the last sighting. So if the target remained at 5 degrees left between 2 rotations of the mirror, the electronics would not output any signal to the control system. Consider a missile fired at right angles to its target. If the missile is flying at the same speed as the target, it should lead it by 45 degrees. Flying to an impact point far in front of where the target was when it was fired. If the missile is traveling 4 times the speed of the target, it should follow an angle about 11 degrees in front. In either case, the missile should keep that angle all the way to interception, which means that the angle that the target makes against the detector is constant. It was this constant angle that the Sidewinder attempted to maintain. This proportional pursuit system is very easy to implement, yet it offers high-performance lead calculation almost for free and can respond to changes in the target's flight path. which is much more efficient and makes the missile lead the target. However, this system also requires the missile to have a fixed roll axis orientation. If the missile spins at all, the timing based on the speed of rotation of the mirror is no longer accurate. Correcting for this spin would normally require some sort of sensor to tell which way is down, and then adding controls to correct it. Instead, small control surfaces were placed at the rear of the missile, with spinning discs on their outer surface. These are known as rollerons. Airflow over the disc spins them to a high speed. If the missile starts to roll, the gyroscopic force of the disc drives the control surface into the airflow, cancelling the motion. Thus, the Sidewinder team replaced a potentially complex control system with a simple mechanical solution.